dark desert highway, cool wind in my hair, warm smell of eucalyptus rising up through the air. Up ahead in the distance, saw a shimmering light. My head grew heavy and my sight grew dim. Had to stop for the night. Welcome to the Hotel California. Such a lovely place, such a lovely face. Plenty of room at the Hotel California. Any time of year, you can find it here. Hello everybody, welcome to this edition of Video Notes for Mr. Flugum's General Chemistry class. That's right folks, I said for Gen Chem. Sorry about my writing there. And we are talking today about compounds vocabulary. So these are some important terms for chemical compounds. So they're things we need to understand about compounds as we move forward with our understanding of chemistry. Okay, so the first term is a relatively simple one. It's one you're familiar with. It's molecule, right? So a molecule is a single unit of a covalent compound. So there's a real key there. If it's a molecule, it's covalent. So there's lots of examples, but two really common ones are water. There's a single water molecule right there. And CO2. There's a single CO2 molecule right there. One C and two O's. Now, just to contrast that with ionic compounds, we need to understand this, right? Ionic compounds do not form molecules, okay? So there isn't really a single unit of an ionic compound, okay? Ionic compounds are the result of this, right? When lots and lots of metal atoms give electrons to lots and lots of non-metal atoms. And then what we get is this crystalline solid, right? So over here is a diagram of, say, what sodium chloride might look like. Okay, it's very crystalline in its structure. It's very rigid, right? And the atoms are stuck in places, right? They're very organized as well. Okay, so remember this, right? Ionic compounds, they form crystalline solids, right? And they do not form molecules. All right, this is just something we need to know in order to further our understanding of molecules and their properties, right? So we have what are called Lewis structures, right? So these are diagrams that show how electrons are shared in covalent compounds, right? So I have a couple of Lewis structures here. Here's CO2 and here's water, okay? So what the lines represent is they represent shared electrons, right? So really what that represents is the two electrons that are being shared between hydrogen and oxygen there, okay? Also here, you see here between the carbon and the oxygen, there's two lines on each side, right? That means that there are 4 electrons being shared between those, right? It's called a double bond, okay? But remember, each line represents 2 electrons. Now the dots represent unshared electrons. So those are electrons that are only for one atom, okay? They're not being shared at all. Alright, now one of the reasons I needed to show you Lewis structures is this. We need to understand this idea here, a coordinate covalent bond. So that's where we have a covalent bond where the two shared electrons come from the same atom. The best example of this I can identify is ammonium. So ammonium, right, is made of nitrogen and 3 and 4 hydrogen atoms, right? Well, here's nitrogen by itself, excuse me. If you notice, it has 3 empty spots, right, where it wants to fill in electrons in order to fulfill the rule of octet, right? So it easily forms this molecule over here, which is called ammonia, right, NH3. However, what happens though is when you take NH3, right, when you take ammonia and you put it in water, it will bond with hydrogen ions. So this H plus will come in and it will attach onto the top of this, right? and it will share those 2 electrons with the nitrogen. Now remember this, H plus has 0 electrons, right? So it's just a proton coming in there. And what happens is it forms a covalent bond where these 2 electrons are shared, but those 2 electrons are both from the nitrogen atom, right? That's called a coordinate covalent bond. It's a vocabulary term that you're going to need to know for the assessment coming up. Alright, next term that we have is electronegativity. So electronegativity is this, right? It's a measure of how much an atom, a specific atom, attracts electrons from other atoms. So what I have here is a periodic table, or at least part of the periodic table of elements, and it shows the electronegativity values for the different elements on the periodic table. So right here, you can see this. Where's the most electronegative elements? Well, the most electronegative is this guy right here, fluorine, right? That is the most electronegative. Okay, and if you notice right around it, you have oxygen, chlorine, right, nitrogen, and sulfur that all have pretty high electronegative values as well. Okay, so that means they like electrons. They take electrons from other atoms. Now, if you look on this periodic table here, where's the least electronegative? Well, least electronegative is over here, right? Specifically rubidium and potassium. Those are the least. Okay, that means they don't really attract electrons from other atoms. They're going to give them away. So the overall trend on the periodic table is this, right? As you move from the lower left, you get least electronegative, and as you move across and up the periodic table, you get more electronegative. Okay? Now this electronegativity is important because it helps us determine lots of things about compounds. Okay folks, so here is our last vocab word and idea for this video notes. Polar molecules. Again, this is something that you'll need to know for our assessment coming up. So a polar molecule is this, right? It's a molecule with a positive side and a negative side. Now what causes this is unequal sharing of electrons. Alright? So even though electrons are shared, not all atoms share them equally. So what causes this polar molecule is, okay, large differences in electronegativity, and also this, how is the molecule shaped? So for example, water right here is a polar molecule. The oxygen side is negative and the hydrogen sides are positive. Okay? And that is because of this. Oxygen is much more electronegative than hydrogen. So even though the electrons are shared, the electrons tend to be shared more by the oxygen. Okay, so that means the electrons spend more time with the oxygen, making it negatively charged, and less time with the hydrogens, making them positively charged. Another example would be this, right? HF, okay, or hydrofluoric acid. Okay. Fluorine is the most electronegative element, right? Which means it's an electron hog. Okay, so around it is going to be what's called an electron-rich region, right? That means that side is going to be negatively charged because the electrons are going to spend most of their time there. And around the hydrogen is an electron-poor region, right? Where it's going to be positively charged. Okay, that makes that a polar molecule. Now an example of something that's not polar would be this. Carbon dioxide, right? Even though there is a difference in electronegativity between carbon and oxygen, if you look at the shape of it, the oxygens are equally distributed on either side of the carbon. So that means this, even though the electrons get pulled away from the carbon, it makes the molecule so there's not a positive side or a negative side, right? In fact, both ends tend to be sort of slightly negatively charged, huh? So this is a non-polar molecule. That's an example of how shape can affect polarity, right? Okay. Well, thanks for tuning in, you guys. Hope you have a good day, and I will see you in class on Thursday or Friday. Bye-bye.